It's a great pleasure for me to start the first lecture, which is devoted to mathematics, and it has a name of the famous mathematician who was working in Prague, Bernarda Bolzana, and he was also one of the first organizer of the Royal Academy of Science and Arts, from which our Learned Society was started. I'm very happy that we can welcome here one of the best mathematicians of this world, Profesor Villani. And also I would like to thank the organizers and especially the men who allow us actually to start this series of lectures and to organize the lecture. Why are you smiling?
I made slight modification while you were...
Sure. Karel Janeček, thank you very much for your donation. Without your contribution, it would be impossible to make it. Thank you very much. I will not bother you anymore, only I am quite surprised how many faces I see here. It's a great Friday Eve, and if so many people came, it tells something about the Profesor Villani and possibly also about the Learned Society of the Republic. Now, let me to ask Professor Bishak, who has organized actually the lecture, and he will introduce Professor Villani, and he will say probably also something about the Bolzano.
Thank you very much. You will also have time to speak, I'm sure. I spoke about Bolzano in the morning already for about half an hour when you had a delay, you know, with your airplane. And I am also happy that there are so many faces, but I must say that in our faculties there was double of these things, weren't they? There was quite really full room, but it's nice that so many people came. I am of course happy that Cedric is here, and Cedric didn't hear my explanation why it is so important that it's a Bolzano lecture. I discovered something in the very recent days. You know when Bolzano was born? On 5th of October, 1781. He was born on 5th of October, 1973. And so that is why he deserved Fields Medal, because he was not yet 40, by doing stability and long-time existence of Landau damping. But I wanted to say a few words why we decided in Learned Society to do these Bolzano lectures. It's something which is common in the more west from our borders. I'm not sure whether you have in France also, say, Henri-Poincaré lectures or not. You have? You have these kind of things, because I know from Cambridge, so there are Sir Arthur Eddington lectures. There is Einstein lectures both in Princeton and in Hebrew University, of course.
We don't have, in France, we don't have an equivalent really of this. We have some lectures associated with prizes.
Perhaps we have Marcel Proust lectures.
Okay, that's normal, because they do it. I think one thing that occurred in France is we went through the Bourbaki.
I see.
In France, when we went through the Bourbaki motion, they tried to kind of remove names and replace them by concepts. Like instead of saying the Bolzano theorem, they would say the theorem of that property. And maybe there was some influence of this. It was related to the fact that we don't have so many lectures with names. We have lectures with names of people. Or maybe because, let me be very arrogant. We have so many great mathematicians in the past that we did not manage to choose.
So why don't you call it French mathematician lectures then? You can say French mathematicians from 20th century, 19th century, and minus 100 years. Well, in any case, we decided with Jan Krajicek and some others that we should do this series of lectures. And actually we succeeded thanks to generosity and kindness of Karel Janeček to start with these Bolzano lectures. It will not be only about mathematics. It will be also astronomers, physicists, etc. And actually, we made a list, thanks to Edda Feyreisel, we came also to your name. And eventually we selected this. And I was also, I'm cosmologist more and relativist, I was supporting this because Bernarda Bolzana was primarily a mathematician. And so I thought, and there is this Bolzano-Cauchy theorem. I was speaking about these convergence proofs in the morning, so I will not speak about them now. But I was very much shocked, and that is something which I should perhaps say because you were not there. Mathematicians invited me in 1981 to speak on their conference on Bolzano. But they wanted me to speak about singularity theorems in general relativity, about black holes, etc. And I thought that I should look at Bolzano stuff. And I looked in Measure of Universe, which is the history of cosmology of 20th century. You know, there is Einstein, Lemaitre, etc. 3 pages are devoted to Bolzano, to his geometry, to bounded spaces, infinite spaces, with amounts, etc. So it's quite fascinating, and one should probably pay more attention to Bolzano also as a physicist. I will not take more of your time. We will also have lectures on Palatsky, and there is a nice coincidence because Palatsky was related to Bolzano, because Palatsky had a daughter who had a daughter who married Rieger, and they had a daughter who wrote first biography of Bolzano. So it's all beautifully interrelated. And Palatsky was a big historian, and the lecture will be in the autumn, so you are invited. It will be most likely also here, and it will be on early Christian archaeology. Let me stop with this, except for one thing which I am sorry to say I have to repeat because I was always fascinated by this part. I think that Karel also didn't hear it. And namely that how Bolzano would save a lot of money of our insurance companies. Who does not speak Czech here, please? It's too many. I will read it in Czech. It will be very brief, and then I will say very quickly in English. Okay, so in German, okay. So, es war so. Povím vám, jak se stal jednou slavný matematik mým lékařem. Bylo to právě o jedných prázdninách, které jsem jako obyčejně trávil v Praze, když mě přepadla velká churavost, jakou jsem nikdy nepocítil, a která se projevila brazením, horečkou a malátností všech údů. Abych se co možná vzchopil, pustil jsem se do euklidových základů a četl jsem nyní poprvé nauku o vztazích, kterou jsem zde našel zpracovanou způsobem pro mě ještě docela novým. Jeho autobiografie. Duchaplnost euklidovského podání působila mi tak živou radost, že jsem se okamžitě cítil opět zdrav. Takže tady máte recept. This is, I'm sorry for those who repeated, this is how Bolzano, when he felt very ill, very sick, so he took Euclides' foundations and immediately became completely healthy. So I am giving it as advice how to save money to our insurance company, you know, for health. Okay, sorry. Well, I'm very happy that Cedric is here and that he will talk to us as beautifully as in the morning he talked to us in the Faculty of Mathematics and Physics. Please.
Thank you. Thank you so much for the introduction, for the great reading. I'm glad that he did not die after reading Euclides. That would have been, you mean our friend when he was sick. And there's an interesting, let me quote, by the way, you talk about Euclides, right? And it's hearing power. There's a quote which I use quite often in popular lectures when I want to tell about the power of mathematics, and it's quoted by Abraham Lincoln. And Lincoln says, I have studied all the books by Euclides until I could prove by memory any of the propositions in the 6 books. I don't know how many people in this room are able to do the same. And Lincoln adds, this way I discovered what proving means. So, which reminds us that mathematics is about proving. It will actually be a nice introduction to this. So let me thank again you for this beautiful invitation. It's a real honor to inaugurate this series of lectures. And I said it this morning, I want to repeat it this afternoon, how happy I was also that you could accommodate for my tricky schedule and find ways so that it would be possible to fit everything in a single day, and in a day which was not the most favorable day. So thank you again for that. And today will be a lecture about various scientific issues, as you can guess from the title, triangles, gases, prices. And men, of course, when I say men here, it means men and women, and it's an allusion to the novel by Steinbeck of Mice and Men. And by this, I mean that we are going to be interested not only in the way, in what science does, but also in the way science works, and what it is, the relation of the people with the science and the creation of new theories. Let us start with an image which I like a lot to comment on the nature of mathematics and the role of the mathematician. There's an allusion about it in my book, by the way, just in passing. This is an illustration of a famous poem by Alfred Lord Tennyson called The Lady of Shalott. I don't know if everybody sees well, or should we put the lights a bit lower? What do you think? Maybe it's okay like this. It's always difficult. Houston? Okay, that's better, no? Yes, super, well done. So this is The Lady of Shalott. That's a poem in which there is this lady from the times of King Arthur, you know, and she's struck by some kind of curse so that she cannot watch anything in the world directly. She can only see things through the reflection of a mirror. And as the story goes, one day she sees Lancelot, who is so handsome that she has to watch him directly. And the curse operates, and she's struck by lightning, she dies, and her dead body drifts in the water. It's a very tragic story. And there has been many speculations about the meaning of this story, also a beautiful song by Lorena McKennitt. And since, as usual, we are allowed to make our guesses when it is poetry and then there is no clue, I like to think that this is an allegory of the mathematician. She is not allowed to work at the world directly, as physicists will do with experiments, but only allowed to examine the world through the reflection. And the reflection is the abstract concepts or abstract theories. Mathematics is a reflection of the world. This is an idea that is present deeply in mathematics and that we will encounter several times in the talk. Let us continue about the nature of mathematics by examining a little bit about what is particular in mathematics through the most famous open problem of all mathematics. Okay, I put a fancy subtitle, Deepest Scientific Mystery of Our Times, or whatever. Riemann hypothesis is this real deep mystery, for sure, which was discovered, imagined by Bernard Riemann, one of the most famous mathematicians ever. And it goes as follows. You define the Riemann zeta function, sum of 1 of n to the s. S is the exponent, and s may be a complex number, and you define this by using the properties of continuation of meromorphic or analytic functions and their rigidity. There is an alternative way to rewrite it in terms of the prime numbers, p. And the conjecture goes like, this function only vanishes at special places, either negative even numbers like -2, -4, -6, and so on, or certain numbers whose real part is equal to 1/2. Here the two curves which are drawn are the real and the imaginary part of this function. On that axis, where real part is equal to 1/2, and where it crosses, where both of them cross the horizontal line, this corresponds to one root of the zeta function. Okay, and the problem is to know if by this way, looking at the negative even numbers and looking at the vertical line, real part equals 1/2, we are able to capture all the roots, that is the vanishing points of the zeta function. Okay, then reaction, if you don't know this problem, is so what? Why do we care about this problem? We care actually very much. There is an anecdote according to which David Hilbert, one of the two best mathematicians of his time for sure, with Henri-Poincaré, said, if I were to sleep for 200 years and then wake up, my first question would be, has someone solved the Riemann hypothesis? So how is it that they care so much? There was some time ago in The Guardian, which is otherwise a great newspaper, an article explaining that if the Riemann hypothesis is solved, it could bring disaster for internet. Now that is a strong statement. Why is that statement? Because Riemann hypothesis is related to prime numbers, as we can see for this formula. But as Riemann understood, information about the behavior of the zeta function gives information about the way prime numbers are distributed. And if this assumption is true, it would mean that prime numbers are distributed in some kind of, in a random way, but in a randomness that you can precisely evaluate. And prime numbers are still very much used in cryptography nowadays, even though there are much better methods, but still it's a very widely used method for cryptography, difficulty to decompose a number into a product of prime numbers. So the reasoning goes, if it is solved, it will be easy for pirates to crack the keys and find the prime numbers which ensure the confidentiality. And of course, if you think about it a little more, you will understand that our journalist friend has not understood anything about it. Because Riemann hypothesis would mean that these prime numbers are kind of randomly distributed, which for sure will not help you the least to discover where they are truly. So it's not that kind of spectacular reason that triggers our interest for the Riemann hypothesis. What is it? First, the fact that it will, if it is true, give some kind of final word to a problem, very simple and very difficult at the same time, which fascinated the ancient Greeks, and that is understanding how the prime numbers are distributed among the integers. That is a beautiful kind of statement and the solution of such an old problem, and the fact that the solution goes through this complex analysis also is a beautiful thing. And there is another thing beautiful, that is that this assumption, this hypothesis, is connected to other fields of mathematics. For instance, one of the famous related problems is the so-called Montgomery-Dyson conjecture, according to which the statistics of the roots of the zeta function is strongly related to the statistics of the eigenvalues of a large random matrix, or let's say the energy levels of a model of large atom, which would give some connection between prime numbers and quantum mechanics in a way. An unexpected connection, a beautiful connection. So, in short, why mathematicians are so interested in this is not because it will have disaster consequences or beauty or strong consequences, but because it will give beautiful solutions and beautiful links. Beauty is one of the main drivers of mathematicians ever since the start. The other thing which reveals the nature of mathematics that it is good to comment on related to the Riemann hypothesis is that in practice this hypothesis is true. I mean, it has been checked by computer simulation again and again ever since computers were made, and it was found that, I don't know, hundreds of billions, the first hundreds of billions of roots of the zeta function are indeed on this vertical line. And still, in the eyes of a mathematician, it doesn't constitute a proof. You see, mathematics is the only field of knowledge in which 100 billions of verifications of your theory do not constitute a proof. And there's something with absoluteness in the way mathematics is done. In physics, you know, general relativity was accepted after a few spectacular verifications, and it was enough to be convinced that it really works. In economics, when you have a theory which can be applied in 3 different cases, it's a great theory that you have. But in mathematics, even 1 million cases, 1 billion cases will not be enough. And that also is part of the special nature and special beauty of mathematics. Now, in mathematics, there are 3 main ways that you can become famous. One is to prove great theorems, of course. One is to find great problems, like this. And the third one is to find great concepts that can be used and reused. And it was the special destiny of Riemann that not only did he find some of the most famous problems in the world of mathematics, but also some of the most fruitful concepts ever. His idea was that by finding the right structures, one could understand the universe. It is, for instance, in his honor that we have named the classical theory of non-Euclidean geometries, Riemannian geometries. In such a geometry, units of length may change from place to place. Geometries may be curved in whichever way you like. And it doesn't mean anything to have a straight line. You know, since Euclides, straight line is the key notion which is at the basis of Euclidean geometry. In non-Euclidean geometry, you don't have straight lines. But instead, you have a notion of line which is the shortest path between 2 points, and this is called the geodesic. And this can be curved in whichever way. And Riemann showed us how to approach this in such a way as to compute the equations of these shortest paths. But also, he gave much more, which was the introduction of the curvature. Curvature had started with Gauss, the master of Riemann, and he developed it into a notion that can be applied to any dimension. Before that, it was just for surfaces. Curvature gives us a fantastic way to classify the non-Euclidean geometries and to understand their behavior. Still to this day, it is the most important object which is studied in non-Euclidean geometry, curvature, and the one which lies at the heart of most theorems. Here is an explanation of curvature in the simple case of surfaces. Curvature will have a sign, curvature will have an amplitude, and to determine whether it is positive or negative, it depends on the behavior of these geodesic lines and whether they tend to get closer, closer than they would in Euclidean geometry, or on the contrary, to separate, to get further apart than they would. In the first case, the curvature is positive. In the second case, it is negative. You can see the difference also when you look at the shape of triangles that is not made of straight lines, of course, but made of curved lines. If the curvature is positive, the triangles will be fat. This is an example. Sphere is the best example of positive curvature. And a fat triangle is one like this, for instance, such that the sum of the angles is always more than 180 degrees, more than pi. In this case, 270 degrees, because these are 3 straight angles. It could be even more, but it can never be less than 180 degrees. On the contrary, this is a picture of negative curvature. The most famous geometry of negative curvature, namely the hyperbolic geometry, in which one representation of it is this disk inside which units of length change from place to place. In this drawing by Escher, it has been materialized by the fact that all the fish have the same length. But because units of length are changing from place to place, we see them with different lengths, but actually their length is the same. So that the distance from one point to another is, roughly speaking, the number of fish which separate these 2 points. And these geodesic curves are materialized by these kind of lines. And when we draw a triangle, geodesic triangle in this geometry, it looks something like this. The sum of the angles is less than 180 degrees. This is a skinny triangle. This is a powerful concept which you can apply in many cases. To see some examples of curvature at work, let us examine some beautiful images. This one is taken from a museum of science in which there was this exhibition of hyperbolic coral reef. That is a hyperbolic coral reef. It's crochet. There are recipes that you can see on the internet on how to knit this. And it looks like an imitation of coral. It's joyful, but it has been made using a simple mathematical rule. Curvature should be negative and constant, according to the formulas found by Gauss and Riemann. Now look at this other picture. This is called a pseudosphere. This one was part of an exhibition of the Cartier Foundation for Contemporary Art in Paris a few years ago. It has a kind of mystic dimension, for sure. But why it was found and discovered by mathematicians is that it is also a geometry of constant negative curvature. And look at this one. The one on the top, the kind of spinning top, part of digital images by Palais and Bernard. This was all made by computer. This, by the way, by sculptor Hiroshi Sugimoto. This one you see also comes from a mathematical problem. It represents the asymptotic state in some problems of mathematical physics. And it is made of various units, and each of these units is of constant negative curvature, and they are glued together. So you see here the power of the concept, where we see 3 different shapes. A geometer would see locally the same geometry. And any theorem you would prove here would be valid here, or on any of these pieces here. And this is a good example to see the power of concepts at work as a way to classify things and nature. And as Henri-Poincaré put it once, mathematics is the art of giving the same name to different things, which is not a definition of mathematics you would necessarily have thought of. Riemann was interested in this as a way to order the mathematical world. And of course, his concepts were explored, extended, improved by others, in particular by Gregorio Ricci, at the beginning of 20th century, who divides the so-called Ricci curvature as a variant of the Riemann curvature, a variant which is adapted to see how volumes are distorted in the non-Euclidean geometry. For instance, when we see distant objects, maybe we have a false impression of how large they are in terms of volume, and Ricci curvature quantifies this. And it was still among mathematicians. But then it was a big shock when, a few years later, with the help of his friend Grossman, Einstein discovered that the Ricci curvature was the keystone, or key cornerstone of his new theory of general relativity. That R, which he is drawing here, could be either for Riemann or for Ricci. It is good that they have the same initial, but it is this curvature. And we see here how, in some sense, the dream of Riemann was becoming reality. By finding the right mathematical concept, he could participate in the understanding of the nature of space and time. Einstein was motivated by pure curiosity for this. But curiosity often turns into technology, or at least sometimes. And it turns out that general relativity is one of the effects that you need to take into account to have accurate GPS positioning. Riemann was not interested at all about GPS. Current users of GPS have never heard of Riemann, but it's okay. Technology is what allows you to profit by the discoveries of science without having to understand how this science works. But still, it's good to remember that behind any technology, there's an enormous amount of work, not just by engineers, but also by scientists and theoreticians who are mainly driven by curiosity. Now, Riemann was very prolific in terms of finding the right concepts. You know, it's very frightening and humbling to look at the lists of topics named after him, all the more than he died before the age of 40. And this power by Riemann of finding deep concepts in all fields of mathematics, to the point that there is no human being nowadays who masters the development of the various Riemann theories. This particular ability in such a short time has made him a very romantic figure in the history of science, or let's say in the history. Actually, let me tell you that one day I met a world-famous rock singer who told me that from time to time she goes on the grave of Riemann for inspiration, showing that there is something deeply artistic in the way scientists work, and that can be also an inspiration for artists. Now, let me also note that going and visiting the graves of these great people is a nice activity. And as you could see this morning, for those who were attending the lecture I was giving, I also like to do it. This is me in the Central Cemetery of Vienna in 2006, near the grave of Boltzmann, and on the grave is written the famous inscription, S is K log W, which is a general statistical definition of entropy given by Boltzmann, a very famous one. Let me tell you a little bit more than I said this morning about the circumstances of this picture. So in 2006, I was invited in Vienna for a celebration of Boltzmann as a specialist of the Boltzmann entropy and Boltzmann equation. And this was 100 years after the tragic suicide of Boltzmann. I knew that he was buried in Vienna, and I knew that the grave was there with the SSK-LOGW inscription, so I made sure that I could find a moment after the talks to go and see the grave. But when I arrived at the central cemetery, I found that I was in trouble because it is huge. It's known that there are famous people buried there, but there is no sign indicated where they are. I had no clue, no guide, and I didn't know where to look for, and I could easily spend the whole night looking for the right grave. So I had to ask my way, and there was a family sitting on a bench nearby. I asked them, do you know where I can find a guide to the famous graves? And they told me, and the father told me, no, there is no guide. Who are you looking for? And then I replied proudly, Boltzmann. And then he said, SSK-LOGW. That gives you an indication of the power of the formula. We know of great formulas for this and that thing, but a formula which can become a password between people in a cemetery who are members of the same sect, you know, it's quite something. So what on earth does it mean, SSK-LOGW, you may ask? Let me try to explain. First, this was what was on Boltzmann's mind, the atomic theory. In those days, atoms were like a dream, and let me remind you that it is only at the beginning of the 20th century that atoms became accepted by a majority of scientists. But already in the 1860s, Maxwell and Boltzmann were fighting to understand the sharp properties of gas, assuming that they are made of a large number of molecules or atoms or whatever. They had no clue about the shape, so they would suppose that these are balls, for instance. No real clue about the interaction, so let us suppose that these are like hard spheres bouncing on each other or something else. And so they would assume that the gas is like a billiard made of a large number of tiny balls that bounce on each other. Like a billiard, but a crazy billiard game which would be made of billions of particles. Okay. Now, each of these particles would be unpredictable, as good as random, because it would collide here and there and so on. But maybe something can be said about the whole dynamics, about the statistics. And Boltzmann and Maxwell were eager to use a statistical modeling for this. So here, F would be the statistical distribution of the molecules of the gas, and with respect to velocity and respect to position. And that would be the problem. Assuming that we know only that statistical distribution, which is in practice what we will be able to know because we'll never be able to have access to these tiny molecules, they thought. What can we say? This replaces physics and gas theory inside the context of one of the most fascinating chapters of science, which is the slow mastering of chance, or statistics and probability. Let us do this long flashback to recall the main chapters of that history. Statistics starts kind of with Jacques Bernoulli. Okay, the date is not really right. It's a bit before that. When Bernoulli, in the letter to Leibniz, talks about statistics and the law of large numbers. And he says things like, assume we toss a coin in the air many times, then the proportion of heads and tails will approach 50%, 50%. And he will say that is intuitive, but very difficult to prove. And indeed, it's not obvious. It's one of the things you learn in an advanced course in probability. Behind this was the idea that if a phenomenon is random, so that you cannot predict the outcome of one experiment, maybe you can predict the statistical outcome of many experiments, so that large number will help you, which is the contrary of the usual. Now comes a fascinating discovery. Abraham de Moivre, around 1730, discovers what we call now the Gaussian law, long before Gauss was born. For the record, de Moivre was a French Protestant who escaped to Great Britain to escape the religious persecution at the moment in which Louis XIV, after Louis XIV had stupidly suppressed the freedom of religion, one of the dark episodes of French history. And de Moivre there made this discovery, that you can find a much more subtle law in the statistics. If you compare the empirical average of your repeated experiments, like the proportion of heads and tails that you really observe, you compare it to the expected average, that would be a true 50%, 50%. There will be some error. That error you cannot predict, but you can predict what will be the distribution of this error. And it will be, with a good approximation, like a Gaussian curve. So here would be zero error. When you go there, the error is increasing. The probability of a small error is very large, but the probability of a large error is very small. And the equation is something like exponential minus x squared for this. And it's always the same, except that it may be more narrow or more shallow, just with some multiplication in the coordinates, in the axis. Now, we are used to this now when we learn about this theorem in probability class, but it is an amazing theorem, totally amazing. Where does this curve come from? Let's continue the story about the slow mastering of chance. In France, at around the same time, Buffon and other people were interested in showing that probability theory is not just about counting heads and tails, but also can be mixed with problems from other fields of science, like geometry. Here is the needle experiment of Buffon. It's an experiment that you can do at home. Take a needle whose length is exactly the separation between two consecutive lines, say on a floor, on wooden floor like this one. And throw the needle on the ground many, many times and count the proportion of times that the needle will meet one of the lines. And if you repeat this experiment many times in a random way, this proportion will approach 2/pi, so something like 2/3. It's remarkable because it shows that randomness has some laws that you cannot escape, and you can find these laws also in some geometric statements. By the way, the geometric nature is captured by the fact that there is pi here appearing. Also, it's remarkable because it's an experiment, like a physics experiment, but which goes contrary to the usual rules of a physics experiment. When you have an experiment to make, you would make sure that when you repeat it, you take the absolute exact same conditions, you know. Here it's the contrary. It will work all the better if you do it in the most, you know, careless way that you can imagine. Throw it in the air or make it spin or whatever. You do it in whatever way and the result of the experiment will be better. That is a special nature of randomness and statistics. The more uncertainty there is in some sense in your individual experiment, and the better will be the statistics for the combination of experiments. It is only around 1810 that Laplace, at last, gives a mathematical proof for the law of errors, which de Moivre had observed. This was an extremely difficult theorem at the time. And it shows, indeed, for any kind of experiment, okay, if you want to be rigorous, you have to precise that the variance of your random variable has to be finite. But for any repeated sequence of experiments, whatever the nature of the experiments, the deviation between the observed average and the theoretical average will be distributed according to Gaussian, with a very good accuracy if the number n of experiments is large, and the typical length here, the typical error, will be of the order of 1 over square root of n. This is for sure one of the most important theorems of all mathematics. It is ubiquitous. It's one of the rare theorems also whose knowledge is useful to know in common life. I mean, in particular, when you have to interpret statistics, polls, as is often the case every day now in France, for instance. And it's good to know which are these error bars and so on. 1846, Adolphe Quetelet in Belgium made this law of random causes popular and showed that it's not only any experiment that Laplace could imagine in which you would have some physics device or whatever. It's also that you find this law of error or law of random causes in problems of human sciences, like, for instance, number of crimes in a city, the fluctuations in the numbers, or the sizes of the people, things like this. And this, by the way, about the variations of crimes, suggested some tricky philosophical questions, like if we can predict from year to year what will be the typical number of crimes that there is in a certain area, where is the freedom of people, to the free will to do or not these crimes. Francis Galton had some strong words to speak of this universal law. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of frequency of error. The law would have been personified by the Greeks and deified if they had known of it. It reigns with serenity and in complete self-effacement amidst the wildest confusion. The huger the mob and the greater the apparent anarchy, the more perfect is its sway. It is the supreme law of unreason. Whenever a large sample of chaotic elements are taken in hand and marshaled in the order of their magnitude, an unsuspected and most beautiful form of regularity proves to have been latent all along. So, this is to place ourselves in a context in which such laws had been shown to appear in many different situations. And this is where we can now go back to the story of Maxwell and Boltzmann. So what they discovered was that you can go a step further in applying these laws in physics. And Boltzmann discovered that you can find a new law which has some information content. A law which describes, which talks about the difficulty which we have of knowing the state of things. It is no accident that this formula for the entropy would be rediscovered later by Claude Shannon, the father of information theory. Here is a quote by Claude Shannon about how he came up with the word entropy for the key notion behind information theory. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. Now, it may be strange that he's hesitating between information and uncertainty, which seem to be contrary of each other. but it's just a question of point of view. The value of an information lies in the a priori uncertainty with respect to the message. If you know in advance what this person will say, maybe because as a professor who always gives the same lecture, or a politician who always repeats the same story, who knows? There is no information when you decipher the message. But if you have no clue in advance, so there is a priori uncertainty, then there is a lot of information in deciphering. When I discussed it with John von Neumann, he had a better idea. You should call it entropy for two reasons. In first place, your uncertainty has been used in statistical mechanics under that name, so it already has a name. In second place, and more important, no one knows what entropy really is. So in a debate, you will always have the advantage. You see, we thought that scientists used to use simple words so that people could understand them more easily. We see that sometimes it's not the case. However, let's try to know what entropy really is, in spite of the curse by von Neumann. Entropy is about the information that we have about a system in an unknown state. A system of which we have just a partial description. In the case of a gas, we have a statistical description. We know which proportion of the gas is here, which proportion is there. That is statistics. And this is less precise than, of course, the full description of all the states of all the particles. So statistical description is less precise, and for any statistical description, there is a large number of possible configurations. In the same way as if you know that in a city, say there has been election for a mayor, and maybe you know that the statistics is 60%, 40% for the two candidates, it leaves an enormous number of possibilities to know who voted for whom. And when you ask somebody a priori, there is a large uncertainty. Now, given the statistics, you look at the number of possibilities, and that in general is a huge number, totally, out of this world, so huge it is. So you call it W, that's the number of possible states, and it's so huge that its value is of no use, so you take its logarithm, which gives you the size. And that you will call the entropy up to multiplication by a very small constant, because even after you've taken the logarithm, it's usually a huge number. Some statistical distributions will be associated to a lot of possibilities in their construction, and so they will be associated with a high uncertainty. That's the high entropy. And some statistical distributions will have low entropy on the contrary. And the discovery of Boltzmann is that through random shocks, entropy always increases. He finds this as a consequence of the so-called Boltzmann equation, describing the behavior of a gas under the atomic hypothesis. This was important not only as a law of physics, but as an explanatory principle for what happens. Let us see, for instance, in this famous experiment, you have gas in the half of a box and nothing here. At the beginning, you know that the gas is confined within half of the box, and then you remove the separation, and we know that the gas will invade the whole box. When we hear about this first, we may think, and sometimes it's explained in this way, that there is a kind of sucking power from the vacuum, like a force, which will attract matter into the vacuum. But Boltzmann tells us there is no force behind this. It's just the power of statistics. And the fact that there are much more ways to realize this configuration in which the gas is spread than there were ways to realize the configuration in which the gas was ordered and on the half box. So this is what should happen as time goes, just by the power of randomness. Now, here is an anecdote so that you will recall this even better. One other cheap joke. So, some time ago, a few years ago, I was invited on some TV show, and when it was after the broadcast, discussing with the presenter, he tells me, and I was like, you know, taking the makeup off or whatever, and he tells me, oh, Profesor Villani, why don't you write on the wall here, like the other guests before you, something which is dear to you? So I wrote, S is K log W, disorder and information. Okay. And he looked at this and he said, this is perfect. Disorder and information could be the motto of our broadcasting channel. And he added, by the way, that it is better than order and disinformation. Now, S is K log W is a beautiful formula, and through it we understand this idea of spreading and order and so on. But it's not practical for computation. Boltzmann found another way to rewrite it in a practical way so that you can compute in terms of the statistics. A formula that you can use if you're an engineer and that you know the particular shape of the distribution and so on. A key step that made it much more practical. And as I was telling you, he was using the theory of partial differential equations to establish his rule of increase of entropy. Let me just flash, for the pleasure of the non-experts' eyes, some of the most beautiful equations that we mathematicians use. Like this Vlasov equation, which was a hero of this morning for the description of galaxies and plasmas. Or the Schrödinger equation, which is the hero of quantum mechanics. Or the Euler equation, the oldest model for fluid mechanics, middle of the 18th century. Or the compressible Navier-Stokes equation. There are some experts in the room, which are very important for description of meteorology and other kinds of phenomena, including fluids. By the way, these equations are also very important in the Hollywood industry. Or equations of reaction diffusion that Alan Turing used to model the appearance of patterns on the skins of animals. Or the Boltzmann equation, which Boltzmann used to prove the law of increase of entropy. This equation predicts with great accuracy the evolution of the statistics of a gas. And if you rethink of our discussion of the statistics, it plays the same role as the law of large numbers. When we toss one coin, we don't know if it will be head or tails, but if we toss 1 billion coins, we know it will be like 500 million head and 500 million tails, something like that. Similarly, when we look at one molecule of gas, we don't know the trajectory that it will have. But when we look at 1 billion of billions of molecules, we know how the evolution of statistics will be. So this is like law of large numbers. And what he discovered is that entropy goes up, as I told you. He computed the increase of entropy, and he showed that the law of maximum entropy is the velocity distribution of Gauss type. So this was remarkable, as it was making the connection between this law of errors, which we saw as so ubiquitous, and this problem of statistical physics, the statistics of the velocities of gases. Now, there is nothing that mathematicians like more than making connections between two fields of science. First, because it's beautiful to find an unexpected link. Second, because it gives precious insight on both fields at the same time. In particular, after the discovery of Boltzmann, long later, it was found some new proofs of the Laplace theorem about the law of errors, which were based on the concept of entropy. Some proofs which are completely different from the usual Fourier transform-based proofs, which we learn in probability class most of the time. So this was a remarkable achievement. Of course, the increase of entropy is an instance of the second law of thermodynamics. But the main difference was that when it was part of thermodynamics, it had been discovered experimentally. And it was a law, something that objects and nature obeys, but we don't know why. Now it became a theorem, something that we understand the reason why. By the way, it's one of the few results in physics which is called a theorem, in this case, H theorem of Boltzmann. Now, in science, as soon as you understand one thing, it leads to several questions, which is the reason why the number of open questions in science never goes down as time passes, but rather increases exponentially fast. And now we have much more problems to solve than our predecessors. So as soon as you have understood what is the maximum entropy, which is the Gaussian distribution, immediately you ask, how fast will we converge to that distribution of maximal entropy? This is a question about the quantitative stability of the gas. And immediately it leads to a whole world of mathematical sophistication. Now, it is in this field precisely that I made what I consider as my first significant contribution. This is when I was 24, 25 years old, with a step in the solution of this so-called Cecchiniani conjecture, which was about understanding the speed of increase of the entropy. This conjecture stated that the amount of increase of entropy instantly is bounded below by a multiple of the difference between the entropy, the maximal entropy, and the entropy of the gas. Simple to state, difficult to prove, as we like it. Also, it's very dear to me because it's associated with a nice memory of work and my first collaboration with Giuseppe Toscani. So this was I had met Toscani in France as I was still a PhD student. He was a specialist of Boltzmann equation, he still is. And I had shown him a big mistake in one of his papers, which is a very good way to become friends. And he invited me back in Pavia to work with him for a couple of weeks. And when I arrived, he told me, I have a crazy idea for the Cecchiniani conjecture, but I have no time because I'm so busy with administration. And please try it, do it like this, put this epsilon, etc. Maybe in the end it will, etc. Okay, I was a PhD student, I had all my time. So I sat down and worked and tried it. And after a few hours, I realized that this idea was completely naive and could in no way lead to the solution. But I noticed there was a beautiful identity in the computations. And that beautiful identity, there was a perfect square popping out of chaotic computations. I thought, this is too good to be useless. And indeed, it was the start of the solution. Aesthetics is a key driver for mathematical research. We have the idea that when we find the beautiful relation, beautiful formula, beautiful identity, it is a good indication that it's the right direction to go. So this was this Cecchiniani conjecture. Let me now, to make a parallel with the previous talk, also say that this Boltzmann equation, Boltzmann theory of entropy, is connected to some of the most important theories in science. Atomic theory, information theory. and also triggers works of mathematicians even to this day, but also is used by engineers. And again, it took 100 years before the discovery by Boltzmann and the use in the industry. But whenever you have a problem involving gas, optimization of the design of a motor, for instance, Boltzmann equation is one of the options that you have to understand what will happen and to make predictions. But there was this huge gap again between the theory and the application. Sometimes, however, okay, now before continuing, let me mention, here I will use a title of a paper by Harold Grad, The Many Faces of Entropy, that after entropy was introduced with a mathematical interpretation by Boltzmann, it became a key tool for many problems of mathematics, some of them having no relation with the physics. Things like information theory I told already, but for instance, the big regularity theorem of Nash for non-smooth diffusion equations relied crucially on the use of entropy. The solution of the Poincaré conjecture by Gregory Perelman, which is arguably the most spectacular achievement of mathematics in 21st century, is also relying in a key way on the notion of entropy, which is very close to one of Boltzmann. Some work by Voiculescu in the non-commutative geometry of C-star algebras, classification of 2-1 von Neumann factors, a problem that you read it, you see that it has no relation whatsoever with gas theory, but it relied on entropy. And it's a good illustration of the fact that the interplay between mathematics and physics has always been rich, and it's not just that mathematicians have tools that physicists can use. It's also very much that mathematics is enriched by concepts which are inspired by physics. Now let me turn to another hero of mine. And in his case, contrary to the other examples, application came at the same time as the theory. In fact, the theory was triggered by the application. So here was Leonid Kantorovich, a great Russian mathematician, working on very abstract subjects and very concrete subjects like atomic bomb or organizing survival when St. Petersburg was besieged by the Nazi army, or working on the organization of taxi fares. He was also one of the first great theoreticians of numerical approximation. But the masterpiece for which he's most remembered is his work in economics. His most famous book, The Best Uses of Economic Resources. When you have resources to use in a certain way, and total amount of resources is limited, and you have to choose between the various ways to use, how should you proceed? It's very interesting to read the book or to browse it even nowadays, in particular for the foreword. Foreword is written by a colleague of his, and about 1/3 of the foreword is devoted to saying that the Kantorovich theory is wrong. That is actually the only case I know of a book in which the foreword say that the book is wrong. And we have to understand the context. Kantorovich was working on trying to give rational foundations to economics. This was very dangerous in his days, in which economics was so full of ideology. Kantorovich was denunciated several times as an enemy of communism and so on. It was said that his theorems had a capitalistic touch, whatever. It was even forbidden to state some of the theorems in public. And he spent a large part of his life fighting against this kind of prejudice. He was very courageous. He never gave up. In 1975, he obtained the Nobel Prize in Economics, which, however, did not end his torments in making his theory applied. let's say that the life of Kantorowicz was strongly influenced by plywood. Now, plywood is nothing sexy, you may say. So what is it that changed his life in there? Well, plywood is made of combination of several kinds of wood that you put together. And one day, these people from the plywood industry came to see Kantorowicz, who was very young but already head of his department. Kantorowicz was very precocious researcher who was full professor at age 22. And they asked him for help. Like, Professor Kantorowicz, we want to reach the target or even to get above the target for our production. You know, in those days it was very important to not be below target. And it's tricky. We are taking wood from this forest, but also wood from that forest. We can transport it in this way. We have one machine that can handle that amount of wood and this amount of that wood, etc. There are many possibilities to organize, and we can't figure out which is the best for us. Nowadays, we would say this is a problem in operational research. And precisely, it is considered that Kantorowicz was the first to solve in practical way such an optimal operational research problem. And this was the birth of linear programming, which nowadays we can discover in high school as exercises. Okay, at least I was lucky to have this kind of exercises in my days of high school, but now in France this has been taken out of the curriculum long ago. I don't know if in this country it is better than the trend that we are enduring. Anyway, what is linear programming? It is when you have a problem in which you want to organize a certain number of unknown quantities. And these quantities have constraints, like for this quantity there is no more than this, or for the sum of this and that there is no more than that. Linear constraints, so they identify a polygon, a convex polygon of the possible configurations. And among all this, you want to determine which one is the best. And for this, you will take your ruler, gosh, I don't have, and you know, swipe it here, put it at the right slope, and swipe the figure until you reach the best point. And when you have 3 or 4 linear constraints, it's good, you can do it by hand. Now in the industry, they may have 100,000 constraints. So you will not solve it by hand, you need a mathematical theory. And Kantorowicz understood that there are general mathematical tools that can be used. Along the way, he also discovered that he could solve with his techniques a very old problem which had been posed by Monge at the end of the 18th century, the optimal transportation or optimal allocation problem. Here is a problem. Imagine that you produce some goods at places x1, x2, x3, x4, and you have to transport them to consumption places y1, y2, y3, y4. But you want to minimize the total transport cost. Maybe some places are difficult to reach. So which should you allocate? A good produced at x2, should they go to y1 or to y2? And so on. So find the best allocation. It's a problem that is tricky, and Kantorowicz, for this, discovered a beautiful duality formula, which I will explain to you in terms of prices. Imagine that you want to solve your optimal allocation problem, minimizing the sum of the cost of transport from the starting point to the final point. On the other hand, arrives a guy who is an expert in transport and tells you, I can handle this for you. I will buy the goods at the producing point, and I will send them back. I will sell them back at the consumption place. We shall just agree on the prices for buying and price for selling, depending on the place. And he adds, I am not a crook, I will never overcharge you, so the difference of price between the starting point and the final point will never be more than the transport cost. Okay, that's a well-calibrated condition. And then you accept the deal, and what the duality theorem tells you is that the minimal amount that you would have spent for the transport problem is the same as the maximal amount that this entrepreneur would have received if the prices are set in an optimal way. And now you see why the Kantorowicz business was dangerous for him. This theorem looks like maximization of the capitalistic profit. And so he was in bad shape for this, even though for him it was clearly in a context of planified economy. Kantorowicz was obsessed by the problem of prices and how can we determine prices in a rational way. Such a tricky problem. Nowadays, it's part of mainstream and you find courses and tutorials that explain you how to apply the Kantorowicz theory and the linear programming, and you have exercises, and it's all under the same banner of linear programming. By the way, one of the most successful optimization theories ever, developed by not only by Kantorowicz, but he was one of the three founding fathers. And they all, again, fall in the same category. It's one of these instances, by the way, in which the solution of the problem appears to you better when you turn to an abstract formulation. Rather than focusing on plywood, focus on some of Ci, Xi, with the Xi unknowns, etc. Okay, these are some of the software which are used to solve this. Okay, now where are we? I told you 3 stories. And we talked about prices with Kantorowicz just moments ago. At the beginning, we talked about shapes of triangles and curvatures and positive curvatures with Riemann. And in between, we talked about the entropy and the spreading of a gas with Boltzmann and statistical mechanics. We saw some parallelisms between some of these adventures. But the reason I chose to tell these 3 stories is much stronger. It's because even though these are different theories developed by different people at different times, they are strongly related. And it was a discovery which was made around 2000. I was lucky enough to be in the small group of people who understood this deep connection, and which gave birth to a very exciting field at the interface between geometry, statistics, and optimization. I will explain you what is this link in rough ways. And I will tell you first that this link was not made because at some point somebody said, oh, I think that this and that, but it was made primarily because there were encounters. It's very often the case. It's good to insist that when ideas meet, it's often because people meet. Also, it was due in large part to randomness. You never plan and know where the interesting progress will come. This cartoon recalls us that there is a big discrepancy between the public perception of science, okay, question, theory, experiment, conclusion, whatever, Nobel Prize, maybe. That is the public perception. And the reality is something like this. You start, but somebody already, what the hell, instrument breaks, not quite expected, amazing result, turned out to be crap. What the hell is going on? Thinking, works, doesn't work, wait, I don't know, oh, that's funny. It makes sense. Oh, no, they figured this out 50 years ago, and again and again. It's a very messy process. And this is for one individual. but then you have to combine this with the messy processes of the other individuals with which the collaboration takes place. Because most of the research nowadays, also in mathematics, is collaborative. So these were my two main collaborators in this story. First, Félix Otto, whom I met in 1998 in France, and then whom I saw again in his university of the time, Santa Barbara, in 1999. Beautiful Californian weather, you know. And secondly, John Lott, whom I met in Berkeley in 2004. This is California again. Beautiful Berkeley campus. And this is the mathematics building, Evans Hall. Famous also because it's very ugly. It's known for this. And I was in 2004 visiting there as a guest of the Miller Institute for Fundamental Research. It was beautiful conditions with the Miller Institute, no research duty, you know, no obligation of research, no obligation of teaching, no obligation of administration. All that they impose on you when you are their guest is that once a week you attend their weekly lunch in which you can discuss. For this, I was paid 3 times my French salary. And still frustrated. When you are in these kinds of buildings, I don't like these kinds of buildings because there is this vertical organization. It's not good for meeting people. In the Berkeley University, which is so famous, there are world stars, but they are all very busy also. So there I was, spending much of my time in my office, wondering what to do, and finding this frustrating, that it was so difficult to collaborate with the people there. And then came John Lott, who was also a visitor, and so not as busy. And Lott came in my office one day. Oh, Profesor Villani, I read your paper with Félix Otto. Yeah, yes, combination of the entropy and the optimal transport problem. And with this, we are going to solve problems in non-Euclidean geometry and this and that open problem and so on. For me, this was a very important moment. Before that, my interests were in analysis and probability, physics. But after that, it was also about geometry. We know in life that sometimes you have one encounter and it may change your life. It's true in research also. It can be one collaborator that you meet by accident and it will change your career. And so we started to work with John, mostly by distance, and we started to work on refounding the theory of Ricci curvature on the basis of the entropy and Kantorovich problem. Let me explain you what was the basis. Let's call it the lazy gas experiment, and let's say that it is an unorthodox view on curvature. It came through the efforts of a small group of people, very international, German, French, Argentinian, Canadian, German, American, German. Not 2 of these people were working in the same lab, all from different labs. And it is a way to define the curvature in such a in language that hopefully would have been pleasing to Boltzmann. Imagine Boltzmann would rise out of the grave and ask, explain me about curvature. You could do it in a classical way, using light distortion, like there is in general relativity. Here is how you could do it. Assume, you want to know whether the curvature is positive. You are at some place, observing some light source, And because it's not Euclidean, the light rays are distorted. So you make an error in your observation. And when you reconstruct the source, thinking you are in the Euclidean world, you make an error. If you always overestimate the surface of the light source, it means that you are in a world of positive curvature. That would be a way to explain it. And now Boltzmann tells you, I don't like these light sources and whatever. I want to hear about gas. And so that is what you would tell him. Imagine that you have a gas in a certain configuration initially. And you prepare a final configuration for the gas. And there is maybe 1 minute that you allow the gas to go from the initial configuration to the final configuration. It's not the Boltzmann equation, because you impose the target. But the gas is lazy, and so he will obey, but in such a way as to minimize the amount of energy which is spent, the in-time integral of the kinetic energy. So the gas, let's do it, go from here to there, and along the way, you measure the spreading of the gas by using the entropy formula of Boltzmann. And if that spreading as a function of time, if that entropy as a function of time is always a concave curve, it means that you live in a world of non-negative curvature. So you see in this case how the three stories are strongly related. Going from from initial configuration to prescribed final configuration is a problem of optimization in the sense of Kantorovich. But measuring the entropy is of statistical nature, like the problems of Boltzmann. And we are, in this way, deciphering a geometric effect, namely the curvature. Now, why is that? Morally, see here, the picture. It's a bit like positive curvature picture. Imagine that you are in a typical positive curvature space that would be the sphere. Starting from matter which is very concentrated on the North Pole, you go to the South Pole, following the meridians maybe. So along the way it will first spread and then concentrate again. That is typical of positive curvature. First spread and then concentrate. When you spread, it's typically an increase of entropy. That is what we learned from gas theory. And precisely, it turns out you're able to measure the spreading with entropy and gets you the right quantity. Of course, there's a bit of miracle in the sense that it's precisely the right notion for the measurement of spreading the entropy. But you need to have some things to marvel on. Now, this is just the basic principle. It was one of the driving concepts behind the big book which I wrote a few years after that, Optimal Transport, Old and New, 1,000-page reference textbook on the optimal transport problem. And this intuition here was the start of our endeavors, of Lot Sturm and myself, to use this as a kind of definition, and to rebuild the theory of Ricci curvature, not from the Riemann curvature, but from the entropy and the optimization. You would say, but that is so complicated. Why do it in this way? The answer is that it's a very robust way, and that it's a way that you can adapt to geometries which are much wilder than the usual Riemannian geometries. Singular spaces. It's more general, and in this way we were able to solve some problems of geometry which had been open for quite a time. Fundamental problems, like when you have the limit of spaces of positive curvature, does the limit also have positive curvature? This kind of basic questions we were able to solve. This is a picture taken from 2013, so 3 to 4 years ago. Karl Theodor Sturm, John Lott, and myself. And this picture was also taken in Berkeley. We were back 9 years after, this time in Mathematical Sciences Research Institute, MSRI. And we were all guests of a special semester activity in Berkeley, which was devoted to variants of optimal transport theory, and delighted to see the confirmation that our theory was in great shape and many developments were being presented. Actually, so many people now, I mean, a couple of dozen researchers are working on this with new theorems appearing every month or so. It's hard to keep track. I gave a lecture on this subject a few months ago. I went through hell to manage to digest all the developments which have been made between the moment in which we founded the theory and the current state of development. But that is a nice thing about mathematics also. You start something, and then if it's a good idea, many people will come to develop these ideas. And sometimes you're jealous because you think, oh, here's a really nice development that I would have loved to prove myself. But after all, they're using my theory and my ideas. It's as if I was associated with this great collective enterprise, you know? Now this is the end of this talk. And let me insist give a final emphasis on these things. I told you in this talk, I also insist on the way people are working together. One key word which was there was the encounter. And the fact that I encountered Otto, the fact that I encountered Lot, and so on. We mathematicians are so convinced of the power of encounters that some of our institutes are devoted to encounters. Such is the case of the MSRI in Berkeley. Such is the case also of Institutu Henri-Poincaré. Well, that's not the only purpose, but its key historic purpose is to serve as place where encounters will occur. And subjects are chosen on a trimestrial basis. This subject, then another subject, the next trimester, then another one. And for each subject, specialists or people who have interest in this will be invited. 100, 200 maybe will come for periods that can be anything between 1 week and 3 months. And there will be some interaction during this time. What? We don't really know. We don't want to planify. There are some courses that will be given and so on. But it is for sure that in many cases, or maybe in most cases, the unplanned interactions which will come from these encounters will be more interesting than what we could have scheduled. And with this emphasis on the importance of the randomness in our way of working, I conclude this Bolzano lecture. Thank you. Thank you very much.
Well, we thank you very much. It was a beautiful lecture. It's a pity that you are leaving tomorrow so early morning. Otherwise, I would take you to Prague Cemetery to make your picture with Bolzano. There is a beautiful grave of Bolzano. There is no formula.
During the night, we cannot do it?
I think, well, we probably would have to climb over the fence. So it's true that the reception was planned already for about 20 minutes ago, but I think that Mrs. Jedináková had arranged that they will keep it for longer. So I think we should allow for a few questions, if there are any questions. Yes, please. Sorry, yeah, that's right. They will...
I can try. My question is linked to the last, about the lab size. When you are talking about the lazy gas, so at the the beginning it's compressed, at the end it's compressed, and in between it seems that it's decompressed, before compressing again. And we said that the decompression corresponds to an increase of the entropy. So it means that then there's a spontaneous decrease.
Yes. Yes, because the evolution, which is used here as a way to understand the curvature, is not the evolution of a natural gas. It's not the natural evolution of a gas. It's a constrained evolution in which you fix the final state. You could not do it with the usual experiment of a gas. It does not make sense. You need special conditions and devices to do these things. But in general, when we talk about evolution equations, there are two main paradigms or two main problems. One problem is you know the initial condition and say it determines also what is the variation. This is so-called the Cauchy problem, specify the initial configuration and see what happens later. And the other problem is you specify the initial condition and you specify a final condition and you see what happens in between. You cannot do it in general for the same evolution equations. And people talk about either the initial value problem or the boundary value problem. Now, in this case, it's still the Boltzmann way to measure the spreading and the Boltzmann way to measure the information. But it's not the Boltzmann evolution, it's not about collisions. And actually, this is a situation in which you can prove that there are no collisions. So it's using the concept of Boltzmann out of the range of the Boltzmann equation and Boltzmann evolution. But again, this is consistent with what I was saying, that once Boltzmann has defined the entropy for a certain purpose, after that, it gets out of the box and will be used for a number of other situations.
Well, let me ask a question. You spoke about many aspects of entropy, but people in relativity now speak about entropy of black holes. They even calculate the states, etc. It's creating all sorts of problems. But I'm wondering, I thought that one really speaks about entropy of black holes, but one does not know what is the entropy of gravitating star cluster. Is it so or not? Just simple Newtonian stuff. But because gravity is attractive, I think there are some problems in this, no?
I confess that I don't remember, even though I remember very well discussion of this problem by a gravity expert, but I don't remember what was the conclusion. It depends on the modeling of a star. There is no problem in defining. There is no problem in defining the entropy of a galaxy because you see it as number of stars, and the stars play the role of microscopic. But entropy depends on what description of the model you have. It's not like energy. It depends on the description that you use. You see what I mean? If you have a complete knowledge of the system, and you know every state and so on, it's, then you have you don't have the notion of entropy. It requires to have a rough description and a precise description. And when you say entropy of a star, you have to specify which is the rough and which is the...
Well, entropy of a star is no problem, I think, of material of star and entropy of neutrinos, etc. I think that what was problem, if I remember correctly, is just entropy of say, cluster of points because of gravity, which is attractive. And so it does not have really usual... It condensates simply in the box. And I think that this caused the problem, but I didn't follow the thing.
Oh, this is when you... No, let me think about it. Is it about...
It doesn't behave like your gas, which goes out and which...
Yeah, but...
you will start to have
okay, you are talking about gravitating, so it must be a free energy rather than entropy, no? Because you take interaction into account?
Which is attractive, however.
So it must be a free energy problem. And then you need some I mean, if you try maybe it's to define it at equilibrium.
Well, I don't know. It will not be an equilibrium because if you have star clusters, so there will be encounters and they could be condensation.
Okay, we will look at this quietly.
Yeah, instead of reception, we can discuss this. Yes. So
maybe Pavel here has the idea of what it is exactly.
Are there questions? Yes, please. Yeah, good. You are.
Yes. Is there a solid way to connect the increase or decrease of entropy with the sign of the curvature of?
You mean a solid way? That's what you say.
A theory that says.
Yeah. There are a number of theorems. It depends on what which ones how you want it to be formulated, but there is very clear theorem that states it's equivalent that, in this case, is Ricci curvature. It's equivalent that Ricci curvature be non-negative or that the entropy be a concave function of time for any initial and starting probability densities that you choose. And it's a very neat theorem. And secondly, you can have some quantification of the way it is. You can be more precise about how much it is concave. If you have, for instance, information on the dimension, or if you have an information on how much it is positive, then you will have a curve. You can be more precise about the curve. And you can actually do it by comparison with a reference space which would have constant curvature and the dimension which corresponds to the bound that you have. So there's a very neat theory for that.
Okay, if there is no further...
Here.
Oh, there are questions.
The comic you made, can it be found somewhere online?
Oh, it's another, about my comics.
Yeah, your comics,
yes.
The comic you made about doing science.
Yeah.
Can I find it somewhere?
Yeah, but it's only in French. Not only in French, it has been translated in Spanish, has been translated in Romanian, but that's all, I'm afraid. But I hope so. If it is not, you write to me and I will yell at the publisher.
Okay, thank you.
It has to be found online, yes, for sure. Yes, I worked with artists on the comics in which the four main heroes, which is historical comics, in which the four main heroes are Werner Heisenberg, Alan Turing, Leo Szilard, and Hugh Dowding.
Okay, thank you.
Okay.
Here.
Yeah.
Hello. It's a question about your Landau damping.
From this morning, yes.
Yes, more to the morning lecture. So the Vlasov equation doesn't raise entropy.
No.
But you have proven that the distribution function approaches some kind of equilibrium.
Yes.
That's kind of disturbing from the thermodynamic point of view.
Now, the key thing is that it depends on the sense of approaches. Now, in the Vlasov equation, what is known experimentally and theoretically is that spontaneously you have the appearance of fast oscillations in the distribution function. These oscillations become finer and finer with time. To be more precise, these are fast oscillations in the velocity variable. They depend on the spatial Fourier mode that you are considering. The typical amplitude is 1 over kt, where k is the Fourier mode you're looking at in the spatial variable and t is time. So it goes like this and this. That's the typical period of these oscillations. And because of these oscillations, in the weak sense, there is convergence to something. That something will have an entropy that can very well be higher than the initial datum. So if you look at the evolution of the distribution, the entropy is constant, still the limit has a higher entropy. And the evolution is only in this weak sense, not in the strong sense. It would be a contradiction. So there is a strong asymmetry between the topology in which you measure closeness in terms of the initial distribution and the perturbation, and closeness in the final sense, in terms of the convergence. When you talk about the perturbation, it's really very close, with a very strong sense, and even you need a lot of smoothness, otherwise the convergence may be very slow or even may not hold at all. So we require perturbation is in a very strong sense, but convergence is in a weak sense. There is a strong asymmetry between the way you measure closeness when it is at initial time or at the large times.
So could you say that, for example, the hydrodynamic entropy increases while the Boltzmann is constant?
Oh. It's okay, there is, there is something like that. Yes. The density, so hydrodynamic entropy will be based on average quantities, velocity average quantities. There is a strong convergence of the spatial density. This you can show. So indeed, the hydrodynamic entropy does increase and does converge to this limit. And it's as if there is a transfer. You know, since you asked the question, I guess you know that the total entropy is the sum of a hydrodynamic part and another part which you can say is purely kinetic. So it's like there is a transfer from one to the other.
Yes, thank you very much indeed. We are most happy.